Okay, today we're talking about the recipe for a square wave. And you might be thinking, a recipe? Well, yeah. Have you ever wondered how digital signals get those super sharp, clean edges? The answer, believe it or not, is hiding inside some of the smoothest, curviest shapes you can imagine. So let's dive in and find out how that works. So that leads us to the big question for today. Can you actually build something with sharp, straight edges using only smooth, curvy waves? I mean, it sounds kind of impossible, right? It's like trying to build a perfect Lego brick using only soft, squishy modeling clay. But as we're about to find out, not only is it possible, it's actually a fundamental concept for understanding, well, pretty much everything around us. See, the way to think about this is that waves are like building blocks. Every complex signal out there, I don't care how jagged or weird it looks, it has a hidden recipe. And that recipe is just a combination of simpler, more fundamental waves. What we're going to do is figure out the recipe for one of the most basic digital shapes there is. All right, to get started, let's just take a look at a signal. We'll call it g of t. Don't worry about the math, t just stands for time. So this is basically just something that wiggles and changes over time. But the real secret, the interesting part, is what it's made of. So let's start with a really simple two-wave recipe. We're just going to combine our first two ingredients. And by putting just two smooth waves together, you're going to see something kind of remarkable start to happen to the shape. Okay, ingredient number one, a basic sine wave just wiggling along at a frequency we'll call f. Simple enough. Ingredient number two, another sine wave, but this one's wiggling 3 times faster, so at frequency 3f, and it's way smaller. It only has 1/3 the strength, or the power, of that first one. And that's it. That's our whole recipe for now. We're just going to add those two together. Now, looking at it this way gives us a totally new perspective on our signal. This is what's called a frequency spectrum. Think of it this way. Instead of watching the wave wiggle over time, we're just looking at its recipe card. And you can see it plain as day. We've got a big spike of power at our main frequency f, and then a much smaller one, exactly 1/3 as big, over at 3f. This chart, it's literally our ingredient list. So what happens when you add just those two smooth, curvy waves together? You get this. It's definitely not a simple curve anymore, is it? Just look at it. The top is already starting to flatten out, and the sides are getting way steeper. It's wild. With just two ingredients, we're already on our way to building a square wave. Okay, that was a pretty good start, but we can definitely do better. So let's see what happens when we start adding more ingredients to our recipe. All right, let's stick with the pattern. We used 1f and 3f, so what's the next odd frequency? Right, 5f. So we're going to add a new sine wave, this one wiggling at 5 times the original speed, and with an even smaller amount of power, just 1/5 to be precise. And would you look at that? The top gets even flatter, the sides get even steeper. We're definitely getting closer. Hey, why stop there, right? Let's add the next one in the sequence, a wave at 7f, with, you guessed it, 1/7 the power. You can see what's happening. Each new wave we add is faster and weaker than the one before it, and its whole job is just to refine the shape. It's like it's sanding down the curves and sharpening up those edges. And we just keep going. We add 9f, then 11f, then 13f, and on and on and on. With every single new odd frequency we throw into the mix, our approximation gets better and better. It just keeps inching closer and closer to that perfect, sharp-edged square wave. So this obviously leads to a big question. How many ingredients does it take to make a perfect square wave? I'm not talking about an approximation, I mean the real deal. Well, the answer is pretty mind-bending. And here it is. This is the big takeaway. A perfect square wave isn't made from 10 waves, or 100, or even 1,000,000. It's made from an infinite sum of them. You heard me right. To get that perfect shape, you need every single odd-numbered frequency, starting from 1f and going all the way up to infinity, with each one getting progressively weaker as it gets faster. So let's just put an official name to what we've been looking at. That ingredient list, that recipe card, is called a frequency spectrum. It's a super powerful tool that lets us take any complex signal, break it down, and see exactly what it's made of, how much power it has at every single individual frequency. At this point, you're probably thinking, okay, cool trick, but so what? Why do we actually care about this recipe? And that's a great question. This is where we get to the real purpose of all this analysis. And here's a hint. It's not actually about rebuilding the wave. Yeah, you heard me. The goal usually isn't to rebuild the original wave. It's to understand what it's made of. In a lot of fields, like audio processing or even computer vision, we don't need to put the signal back together. We just need to know the recipe. That's the key. And that's because looking at the frequency spectrum often tells us everything we really need to know. Our goal is just to understand the signal's frequency content. So what we focus on is the amount or the power of each frequency. And for a lot of applications, we can totally ignore other details like the exact timing or phase of each little wave. Just knowing the power at each frequency, that alone is often the critical piece of the puzzle. Which really leaves us with one last big thought. If we can build something as sharp and, well, unnatural as a perfect square wave using just a bunch of simple, smooth curves, what else is hiding out there? What hidden recipes are tucked away inside the sound of your own voice, or in a digital photo, or even in the light coming from a distant star? It really makes you think, doesn't it? This whole analysis, it's just the beginning.